everybody. I am Tejaswi from Mechatronics. Today I would like to discuss general purpose interface bus with high speed 488. This general purpose interface bus is also called as IEEE Digital Communications Bus Specification. Here we should notice one point, that is, it is entirely based on the digital communication. That is, it doesn't allow the analog communication. That is, the bits, the data which we are transferring is only based on the zeros and ones, but not on the 0 volts and 5 volts. Also, this IEEE 488 was first basically created as HPIB, that is, Hewlett-Packard Interface Bus, which is commonly called as General Purpose Interface Bus. This is it was subjected to several standards. Basically, it was adopted from IEEE 488, and thus the revised version of IEEE 488 was 488.1, and it is used for electronic parameter calculation, and then later it was further revised and IEEE 488.2 was obtained. This general purpose interface bus is widely used for enabling electronics test equipment to be controlled remotely. That is, electronic equipments which are far away can be remotely controlled by using one controller system. As I have clearly mentioned, this is a GPIB cable. The length of the GPIB cable, that is the communication that the GPIB cable can or communicate, is only 20 meters. And the main advantage of this GPIB cable is it can connect 15 instruments with a maximum bus length but should not exceed 20 meters. Basically, this GPIB performs the main functions of GPIB bus of 3, that is controller, listener and talker. First, let us discuss about the controller. The controller is the entity that controls the operation of the bus. It is usually a computer and it signals that instruments ought to perform the various functions. We should consider one important point, that is, many controllers can be interfaced on a single line, but one controller should be operated only once. That is, one controller at particular time. And the control process is basically placed on non-movable system. The next thing is listener. Listener is an entity connected to the bus that accepts instructions from the bus. We should notice that listener only accepts the instructions. That is, it does not function like it does not give any instructions to the system. It only accepts the instructions from the bus. Talker. This is an entity on the bus that issues instructions data onto the bus. Unlike listener, the talker issues the instructions, that it gives output instructions to the bus. Let us take the example of a voltmeter. In voltmeter, this is a control device. This acts as a bus. This will act as a listener when it is being set up, and then when it is returning the data, it will act as a talker, known as a voltmeter takes the input from the system and gives the output to the system, which acts as a talker and a listener. These are the 3 functions of the GPIB bus. The main advantages of this GPIB bus is it is very simple and standard hardware interface, that is, it can be easily implemented. Interface present on many bench instruments. This can be easy instruments. Rug connectors and connectors used, that is, although the systems are installed previously, it can be easily implemented on an already existing system. Possible to connect multiple instruments to a single controller. As I said previously, many systems, that is 15 systems, can be connected parallelly and can be processed, but the length should not exceed 20 meters. As you should see on the boards, will be having disadvantages. The main disadvantages are providing length up to 20 meters and it can connect up to 15 systems. It is holding some bulky connectors, that is many connectors are needed to connect the systems. Stability is poor, which often result of the bulky cables. Also it gives low bandwidth, it uses low bandwidth, but it is slow compared to modern interfaces. 422 does not mandate a command language, that is SCPI used in later implementations but not included in all instruments. Now let us discuss about HS488, that is high speed 488 bus. This is more advantageous when compared with general purpose interface bus. Like normal transfer rates on the general purpose interface bus are only order of the 1 megabytes per second, whereas high speed 488 bus can achieve transfer rates up to 8 megabytes. That is, it can transfer the data rate up to 8 megabytes per second. These are having some protocols. The first one is high speed general purpose interface bus handshake protocol. This protocol is mainly derived, that is patented by National Instruments. That is, National Instruments developed this handshake protocol. This has developed the patented high speed handshake protocol, also called as HS488, to increase the data transfer rate of a GPIB system. That is, while using GPIB, we can transmit only 1 megabytes per second, whereas if you need to transfer more data rate with accurate and more speed, we can use high speed general purpose interface bus handshake protocol. As we are having in the general purpose interface bus, we are also having some IEEE standards for high speed general purpose interface bus also. This high speed 488 acts as a superset of the IEEE 488 standards for the entire system. Now we can see the timing diagram for IEEE 488 handshake. We will be having three main signals, that is data valid, NRFD and NDAC. These three signals are the basic key elements of the IEEE 488 handshake, which we have discussed earlier. NRFD first propagates to the talker, that is not ready for data. That is, the talker propagates NRFD data to the listener. DAV is the data valid signal which propagates to all the listeners. Listeners then accept the propagated signal talker, and then it accepts the byte which it is to be transmitted, and this listener asserts another signal called no data accepted. That is, it is not ready for any data to be accepted as it has already received the data sent by the talker. Now then again this listener propagates back to the talker that it is not ready for any data to be accepted, since it already accepted one byte of data or something else which the talker already sent. As I have shown previously, T1 is the settling time. That is, the T1 is the settling time for data valid before asserting. This is high speed 488 handshake. Let us have a glance of comparison between IEEE 488 handshake and HS 488 handshake. The function of the key elements of which I have mentioned earlier was same, but the only difference is HS 488 throughput. How it increases system throughput? This can be achieved only by removing the propagation delays associated with the three-wire handshake. That is, while we can see in the timing diagram of IEEE 488 handshake, we will be having some propagation delays during the transmission of the byte. That can be eliminated in HS 488 handshake by implementing all the key elements like data valid, not ready for data, and no data accepted. Next thing is high speed 488 data transfer flow control. Usually this implements two key elements, that is not ready for data and NRFD. that is no data accepted. Usually HS488 can transfer data at up to 8 megabytes per second. For a fully loaded system, as I mentioned earlier, it carries 15 devices and 15 meters of cable. HS488 transfer rates can reach 1.5 megabytes per second.